Hello, Professor Elliott again, and this will be an overview to the Darlington Amplifier. If you have not seen my companion video on the common emitter amplifier, I would suggest you go review it first. You don't have to, but I think it's better that way. But anyway, I have other videos on my channel about the detailed calculations, doing it the quote unquote the proper way. This is just simply an overview, and hopefully, if you're interested in these amplifiers, that you will find this helpful. The Darlington amplifier, its purpose in life is twofold. One, it has a very large current gain, both on the AC and DC side. But since we're using this as an amplifier, let's talk about that. Now, a full analysis of this is well beyond my objective for today, and it would require me to take you through the Thevenin's theorem, the full AC model, input impedance, output impedance, the whole 9 yards. Once you get to that point, it's then fairly simple to show you the gain, the current gain, which is simply the ratio between the AC current drawn from the source to the AC current delivered to the load. But that's far beyond what I have planned for today. So current gain, it can provide lots of AC current gain or DC current gain. It also has a fairly large input impedance and a very low output impedance, so it's very a handy circuit to use when you want to buffer interface two different circuits with very different impedances, whereby connecting them together you might cause unnecessary loading. But anyway, so the arrangement as far as the DC biasing goes, it's still the voltage divider, and you will see the base voltage of transistor Q1. Notice there's two transistors, we'll talk about that. The base voltage of Q1, VBE1, that is the voltage from the base of Q1 to the common ground, which is the voltage across resistor R2. So that is this voltage right there. And that voltage is determined by the ratio between R1 and R2. Now, as I tell my students, it's a simple matter of picking two ratios on the resistance values of R1 and R2. The trouble is those values impact other things, so they can't be chosen at random, so it's always a compromise. But anyway, so we have our base voltage of Q1, which is VR2, okay? VR2. So as I don't have any values here, and that was intentional, look at my other videos if you want that. If this voltage here was 6 volts, okay, I'm sorry, I'm still using my mouse, so okay, was 6 volts, then what would be then the voltage at the emitter down here? What's 0.7 volts less? So this point here would be 5.3, and then we will lose another 0.7 down here for this base to emitter junction. So Then now we're down to this formula here, which says the emitter voltage here is the voltage at the base here minus 1, minus 2, minus 2 diode drops, or a nominal 0.7. So if that is 6 volts, minus 1 would get us 5, minus 4, so that would be what? 4.6 volts, roughly. Okay. The purpose of having two transistors, that's what gives us the current gain. So whether you're looking at the beta AC, the AC current gain, or the beta DC, the DC current gain, by cascading them together, the betas actually, they multiply. So that's why whether on the AC or DC, we can have lots of current in the collector and only a little bit of current in the base of Q1. Resistor RE is the resistance called the emitter resistor. Notice that the collectors of both transistor 1 and 2 are connected together and they go to VCC. So the collector voltage VC is simply whatever that is. Okay? All the interesting stuff happens on Q2, because Q2 is the one that's ultimately carrying the load current. And the function of Q1 is really just to provide the base current. Look at the emitter of Q1. The emitter of Q1, look, boom. It's providing the base current to Q2. Okay. So we start with our base voltage of Q1. Just use the voltage divider to solve for R2, V2 across R2. Minus 2.7 volt drops, we arrive with 0.7 volts on the emitter. Divide that by the emitter resistance. Again, I have other videos on this. Much more detail. That gives you the emitter current. Okay. All the key parameters, current and voltage, are marked on the drawing, and I formally identified them for you there. Okay. Power dissipation. Q2 is really the most important of the transistors. It's handling the load current. And if you're handling a lot of current, that means those transistors, they're going to be power transistors, possibly heat sinked. They need to dissipate the power. So the Q2 power dissipation, PD Q2, is simply VCE2, the voltage collector to emitter, multiplied by the current. That's, go back to your basic electrical theory. That's one of the power equations. Okay. The amplifier voltage gain, in general terms, look at my other videos, I think it's called Solving the Darlington Amplifier, if you want the full show. Is simply the ratio between the output and the input. Unlike the common emitter amplifier, there is no phase shift at reasonable frequencies. We're not talking about high frequencies effects, but the input and output sine waves are in phase. The output voltage is ideally equal to 1, so it's not actually providing current voltage gain, it's amplifying the current. Okay. So I've used not exactly like this, but the Darlington arrangement, which I'll probably do in another video, on a circuit that I built to drive a relay, and I needed to have enough current to drive the coil, but the transistor could not provide that much on its own, so I used two of them. But that's for another day. The load line, it's the same discussion as in my last video, okay, where this is the saturation current. Assume VCE, what we're talking here, is equal to 0, then that current is just this divided by that. VCE off, oh, I really should get out my sketch tablet for the next one, is the open switch. The current is going to be 0, so all the voltage is across the collector to emitter. Okay, that's another video. Hope it helps. Have a blessed day. And today, by the way, if you're interested, is Saturday, May 3rd.